Welcome to another video on Circuits Decoded. Today we'll talk about feedback circuits. If you have ever tried to analyze a feedback circuit and wondered where to open the loop, you are not alone. Loop gain, also known as return ratio, is an important quantity required to estimate closed loop parameters such as input and output impedances, stability, etc. So getting the return ratio calculation wrong will lead to an incorrect result. Today we'll discuss a more general way for where and how to open a unilateral loop for loop gain analysis. First, let's revisit the common way to analyze feedback loops. Shown here is a simple single loop feedback circuit where the control current source creates a voltage across Z2, which in turn controls the current. To find the loop gain, what we usually do is break the loop at any given point and apply a test voltage across the impedance Z2 and find the return voltage across Z1. However, one must take the loading into account. For example, in the original circuit, we see that Z2 was in parallel with Z1. So to correctly find the loop gain, we need to add Z2 in parallel with Z1 after the loop is broken. Then we apply simple KVL rules to find the loop gain as shown here. This method works well as long as we can correctly find Z2. However, Z2 is not always obvious or straightforward to calculate. Another approach I find more useful is the Rosenstark's open short method, as it does not require us to change the circuit after breaking the loop. However, this is a two-step process, which requires us to find both voltage and current loop gains. So firstly, we break the loop at any point and apply test voltage Vt as before, and find the return voltage Vr. This gives the voltage loop gain Tv, which is equal to minus of Vr over Vt, which is equal to Gm times Z1. Next, we apply a test current source It at the same location and short circuit the other end and find the short circuit current IR. This gives the current loop gain Ti, which is simply negative of IR over IT, which is equal to Gm times Z2. Please be mindful of the direction of IR. Now, according to Rosenstark's technique, the final loop gain can be found by simply adding the reciprocals of Tv and Ti. Now, the final loop gain T is equal to Gm times Z1 parallel Z2, which matches with our previous result. The good thing about Rosenstark's technique is that we can break the loop at any point and not care about the loading. Let's test the correctness of this technique with an example. Shown here is a simple voltage-voltage feedback amplifier, and we need to find the loop gain of this circuit. Let's break the loop at the gate of M2 and apply test voltage Vt and load Vr with the appropriate loading. We can see that the load resistor here is infinity and do not change the loading at Vr. Now to find the loop gain, we first need to find Rf, which is simply given as R1 plus the parallel combination of R2 and 1 over Gm1. Next, to find Vr, we need to find the part of the current as flowing through M1 and multiply it with R3. To find the current, we can do a simple current division analysis as shown here. The loop gain is simply the ratio of Vr over Vt and can be given as shown in this expression. Now we substitute Rf in this expression and further simplify it as shown in equation 1. Let's try to find the same loop gain using the Rosenstark's method. This time, let's pick a different breakpoint location. As shown here, the source of M1 is chosen. First, we need to find the voltage loop gain. So we apply a test voltage source at the source of M1. By doing simple small signal analysis, we can find Vx as Gm times Vt times R3. And Vr is simply the output of the following common source stage, which is negative of Gm2 times Vx times R4. The loop gain is simply the ratio of Vr over Vt, which is the product of Gm1, Gm2, R3, and R4. Next, we need to find the current gain. To find the current gain, we replace the test voltage source with the test current source It and short circuit the other end of R1 as shown here. We then need to find Vx and the short circuit current IR as shown in this expression. Now I'm not going into the details of these calculations, but if you're a bit rusty on small signal analysis, I encourage you to pause this video and try to derive these expressions on your own. Now by taking the ratio of IR and IT, we can find the loop current gain as shown in this expression. Now using the Rosenstark's loop gain equation, we can find the reciprocal of the overall loop gain as shown in this expression. Taking its inverse, we can get the final loop gain value T as shown here. By comparing this result with the one derived using the common technique, we see that both results are identical. Now Rosenstark's method allows us to open the loop at any point. However, we can ask ourselves, is there a preferred location? And the answer is yes. If we see the loop gain equation 1 over T, we see that there are two terms, 1 over TV and 1 over Ti. So if any of these terms becomes 0, we can work with either voltage gain or current gain. In fact, a convenient spot to apply the test signals is at any high impedance node where the current gain is very large. In our circuit example, this location is at the gate of M2, where the current gain is infinity. So finding the voltage gain is sufficient. You can watch Ali Hazimiri's video if you want to know more about this type of loop analysis. I have shared the video link in the description box below. So that's it for this video. If you like this video, don't forget to share and subscribe. And again, thanks for watching, and I'll see you in the next one.